Methanol is often the fifth or sixth item on the operating expense budgets for many oil and gas production companies, yet there is generally a lack of strict controls associated with 1. Determining the need for methanol, and 2. Establishing and optimizing the daily methanol injection rates. Our focus has been on methanol optimization since 1994, when the industry first seemed to realize that excessive overinjection of methanol was a contributing factor to an increasing number of top-of-the-line corrosion failure events. We recognize methanol is not a pharmaceutical-grade product. It has trace levels of contamination and impurities, such as low levels of strong organic acids, such as formic hydrofluoric and hydrochloric. In pipelines with excessive injection of methanol, droplets condense and rain within the regions along the pipeline and cause a chemical corrosion attack within the top hemisphere of the pipeline. If the methanol rain is sustained in these localized regions, the corrosion rate can cause a pipeline failure typically within 1 to 2 years of exposure, 40 to 50 times faster than the corrosion associated with the normal produced fluids. When overinjection of methanol causes corrosion, the failure typically occurs on a slightly declining section of the pipeline following a region of moderate inclination. The failure occurs here because it is the region along the pipeline where the shear stress of the flowing gas stream applied onto the pipeline surfaces are the weakest. The flowing gas stream in these situations is not capable of ripping the droplets away from the pipeline surface, and the corrosion mechanism is sustained. We recognize hydrates are complex. We explain them by referring to a hydrate triangle. 3 conditions must be in place for a hydrate to form within a pipeline. Unlike most calculators, we consider both a thermodynamic tendency and whether the flowing conditions within the pipeline are appropriate to support the kinetics of the hydrate formation triangle. We calculate if regions of thick water film accumulation are likely to occur within the pipeline. Regions of stagnant water accumulation are essential to support the hydrate formation because they create localized pressure losses and generate a microhaze of free water droplets, 2 ingredients absolutely necessary to support the formation of the hydrate plug. This is a schematic that provides a summary of how we execute our projects. We gather pipeline physical and operating data and characterize the properties of the water film transport. We then calculate the hydrate formation temperature using the Noursock model. We use the Hammerschmidt equation to establish theoretical methanol injection requirements necessary to suppress the hydrate formation temperature below the lowest pipeline operating temperature. Because we calculate the water film behavior, we know how much in situ water resides within the pipeline at steady state conditions. By overlaying the pigging frequency onto the operating conditions of the pipeline, we establish if operational pigging is an aid to hydrate prevention. This is an overview of the first page of our hydrate and methanol optimization calculator. It provides a summary of the pipeline static information, production allocation volumes of oil, water, and gas, pressure and temperature and gas velocity profiles, a list of the pigging intervals being performed on each pipeline by field operations teams, the in situ water volumes for each pipeline should steady state operations be achieved. By considering the total daily water volume, calculated days to reach steady state operation. This column is a summary of the benefits of pigging to the prevention of the water from reaching steady state. The negative number indicates the days at which the pigging frequency prevents steady state from forming, and the positive numbers indicate the days in between pigging where the steady state of water fill is actually achieved. The effects of operational pigging on disruption of steady state operations is translated into a pigging benefit index. The higher the index, the more likely the pigging frequencies being applied by field operations are preventing hydrate formation. A comparison between the required methanol and the actual methanol being injected by field operations. There is a feature where the user can select an individual pipeline and receive a detailed engineering assessment calculation report. The user has the ability to apply a global default or a bias onto the calculated hydrate temperatures in order to provide a safety factor or a sensitivity on the overall methanol requirement. In this case, application of a positive 3 degree bias on top of hydrate calculation temperature results in an increase of 20% of field injection requirements for methanol. The user can also make a global bias adjustment to the calculated cold gas temperatures for each of the pipelines for the situations where there's extreme cold ambient temperatures. In this case, a 25% factor, or a cooling of the gas by 25% of calculated temperature, results in an increase of 30% demand on field injection of methanol. The owner has the opportunity through the data validation sheet to override any of the calculated values and to make adjustments as changes occur in the future to temperature, actual field injection of methanol, to operating pressures in the well field, and making adjustments to the production allocation. Why not just give us a call and we can discuss the terms to complete a project for your company? Thank you for watching this video post.